So, here we already seen that the smoke is a combination of flue gases, that is the combustion products like CO, CO2, H2O etc., plus some carbonaceous particles such as soot. So, basically what happens is, if you take say for example a candle flame, as I discussed earlier, in a slow burning situation, that the smoke will not appear in the tip of the candle flame. But if you have a bigger candle etc., or if you do not have good aeration, then you will see that the tip of the candle flame opens up and smoke comes out. That means there is a minimum burning rate of a fuel which will constitute to formation of smoke. What happens is, the soot particles will be produced when unsaturated hydrocarbons are present in the fuel. Now, the soot particles which are formed, they will agglomerate, that is they will grow in size, then they will also be oxidized within the flame. But this will happen only when the burning rate is smaller and enough oxygen is available from the ambient. But if you increase the burning rate to a critical point, say for example I inject say propane through a burner, circular burner, at low flow rates you will form a flame. So, for example the flame will be closed like this, and there will be no smoke which will come out of this. But if you increase the flow rate to a critical value, then the tip of the flame opens and the smoke comes out. That means the soot particles will come out without being oxidized. So, the minimum flow rate at which you can visualize your visible smoke, that is called smoke point. Okay. So, as I told you, smoke is nothing but the soot particles along with carbon monoxide, nitric oxides, carbon dioxide, nitrogen, water vapor and so on. But still more, if you burn plastic type of materials, dioxins type of harmful pollutants can also be formed. So, that is one of the important characteristic. What is the problem with smoke is, basically within a compartment if there is a fire, the visibility of the firefighters etc. will be decreased. Not even that, the occupants of the compartment will not be able to visualize what is happening. So, that is the problem with the smoke. The smoke actually rises up, hits the ceiling, then descends down, and this smoke layer, if it is hot enough, say if temperature of that is about 600 degrees centigrade, then this may ignite the other commodities of the room, causing flashover. So, now we will move on to definitions related to fire detection and fire suppression. So, when there is a fire, first thing is we have to as soon as possible detect the fire. For that we have three types of sensors. One is the heat sensor, and the second one is the smoke sensor, and the third one is the CO sensor. Basically, the heat sensor, these will be located in the ceiling, and if you have the detector, the temperature of the detector increased beyond a particular value. Say for example, if the ambient temperature is 25 degrees, if due to the fire the detector's temperature reaches say 20 Kelvin or 30 Kelvin more than the ambient temperature, or the rate at which the temperature increases is also recorded, based upon that it will say a fire is detected. Smoke sensor on the other hand will be optical type of devices, say photoelectric based devices. We will see about this later. So, now what happens is, when there is a light source and a receiver, in ordinary atmosphere of air, there will be some amount of light which is given out by the source and received by the receiver. But in the presence of smoke, the received light will be lesser. If the threshold decreases beyond a certain level, the smoke is said to be present in the room and the smoke will be detected. That means the fire will be detected. CO on the other hand, a fine sensors are used. CO normally is formed due to incomplete combustion of some fuels like hydrocarbon fuels. There the CO sensors will detect ppm levels of CO, and normally in atmosphere there will be no CO. So, if there are some amount of CO, say more than 500 ppm, 1000 ppm etc., then it will produce an alarm. So, these detectors normally will detect using some property and produce an alarm. Also, these detectors are connected with devices like sprinklers, which are water based systems. That means they are connected to hydrants and water supplies, so that once the fire is detected, the sprinklers will be activated. So, the first an alarm will be produced, so that to caution the occupants. Then after that the sprinkler will be, so within certain time period, because you are allowed the occupants to just go out of the enclosure of the room. After that, within a small time period, sprinklers will be activated, and you will see that water jet will be coming out or water particles will be coming out. Basically, this cannot easily quench the fire, but it will delay the fire spreading to a very high level, or it will reduce the risk of flashback. Now, the time for detection depends upon a important characteristic called response time parameter. Again, properties of the detector itself. Okay. So, now we will see about these properties, how much temperature rise is required or rate of rise is required, or what is the concentration of smoke will be able to make the detector detect the smoke, and so on. We will see that. So, in general we have what is called response time index, which is also a characteristic of a detector that will be used. Now, fire suppression, we have seen about the fire triangle: fuel, oxidizer and temperature or heat. Now, you reduce your temperature, heat feedback to the condensed fuel reduces, or the rate of reaction also can reduce, you reduce the temperature. So, that is one of the way to suppress the fire. Similarly, the oxygen should be diluted. So, you can, if you use water, the water will vaporize, and the water vapor will reduce the concentration of the oxygen. That is another way. Similarly, the fuel which is coming out of a solid surface or a liquid surface basically can be arrested by using suitable suppressants. For example, in the case of solid fuel, water itself will be a very good suppressant. But in the case of liquid fuel, we normally use foams. So, we have seen the categorization of the fuel sources and how to suppress them. So, now if you take say sprinklers, then temperature and oxygen concentration will be reduced by them, because you can use, but please understand, you cannot use it for electrical fires or liquid fuel fires. Now, one more thing is there, use some halons. They will directly affect the chemical reactions. We will also talk about that, but actually speaking, the halons are not usable nowadays because of environmental issues. As I told you, for liquid fuel fires, you have to use foams, which will actually spread over the liquid fuel surface and inhibit the generation of fuel vapors. So, these are the definitions related to the fire detection and suppression. Then, flammability limits. These are standard tests. Flammability tests are standard tests, which actually will be used to evaluate the fire related aspects of the materials. So, flammability tests are carried out to evaluate the several fire related aspects of a material. What are they? Ignitability. See, for example, if I use a cardboard, or say for example, if you use a fiber based lining for walls etc., they are easily ignitable, unless otherwise you dope it with some fire resistant material or substance. Now, second one is flame spread rate. How fast the flame can spread after the ignition occurs. Okay, in one corner ignition can occur. How fast the flame can spread, that is a hazard for us. So, that is also quantified by the flammability tests. Then mass burning rate. Once the flame spreads over the surface, how fast it consumes, the fire or flame consumes the material underneath it. Of course, the rate of burning and heat release rate are connected to each other. How fast the material burns, based upon its calorific value, the heat release rate will be got. Mass burning rate into heat of combustion or calorific value will give you the heat release rate. So, to do the flammability test, we have several standards. One of the American standard is ASTM type of standards, and we also have several European standards and so on. Then that apparatus what we use basically are classified into two types. One is called flame propagation apparatus, FPA. Second one is called cone calorimeter. So, we will be able to see about these things in a little while. So, let us go to cone calorimeter. In cone calorimeter, what we do is, we have a horizontal table in which a specimen is kept. Specimen can be a liquid fuel in a bowl or a solid fuel itself, etc. And there is a conical heater. Okay, that means you can see that the heater will be imported within a section of a cone as shown here, and it will have coils around it, so that it actually gives the heat flux to the specimen. Whatever rate you want, you can adjust the current flow through the cone heater such that you will get the required heat flux at the specimen point. You can calibrate it and know by using the exact current circulation how much heat flux you impart to the material. You can also adjust the distance between the cone heater and the specimen bed or the specimen table. Now, for this is the photograph in the right hand side where you have the red hot cone and the sample is kept in this. You can see some gases coming out of the sample, that is the pyrolysis gases coming out of the sample. And when you want to conduct ignition test, I will keep a piloted ignition source like spark plug at a certain distance, again based upon the standards. Above the specimen surface, I will keep the source, the ignition source like spark plug. The heating will be continued so that the pyrolysis takes place, gas comes out, mixes with the ambient air, and this ignition source will cause an ignition. So, once ignition occurs, then a flame will be formed over the surface. That means I have to increase the temperature of the specimen if it is a liquid fuel to a fire point, if it is a solid fuel to a temperature beyond the pyrolysis temperature. Now, the cone, top part of the cone is hollow, that means the product gas which are formed, the fire gases will go out of the cone through its top surface which is hollow, then it moves through a hood. This hood basically has all types of instrumentations, like for example, it has a gas sampling port through which some gases can be extracted and we can analyze what types of gases are produced. So, you have to extract some amount of gas, so some volume, and we can take it to the, so cool it, remove the water and take it to the gas analyzer. Then smoke meter, how much amount of smoke is there, that also can be detected. So, laser type of smoke meters can be used or optical types also can be used. Then actually this blower actually sucks this hot gases basically, so that the hot gas only goes through this hood. Now, the flow rate of this gases can also be measured by by putting an orifice plate. So, there are standards to design the hood, the pipings, the orifice plate, the port sizes, etc. So, this is about the cone calorimeter. So, I can now do the critical heat flux which is required for causing ignition, because if I set a given temperature for the cone surface, a particular amount of heat flux will be imparted to the specimen, but that may not be able to cause the ignition even though the spark is present. That means the heat flux has to increase to a critical value. Now, the critical heat flux, under the presence of critical heat flux, if you have the spark at a given distance, then you will be able to ignite it. If the spark is moved very close to the specimen, it will be fuel rich area, then you will not be able to have the ignition. If it is too much away from the surface also, it will be, there will be more air than the fuel. So, the spark actually is located in a position where some good mixing has happened and flammable mixture is available for this to burn due to the spark ignition. So, now other than this, so what I do here, ignition critical heat flux, ignition temperature, I can also monitor the temperature of the specimen. So, I can get the temperature at which the ignition occurs, for the surface temperature, etc. Then I can just burn this, and I determine the rate at which the mass is lost using a load cell which is in the bottom. If the table is put on a load cell, I know mass as a function of time, how it reduces. So, I will find what is called mass loss rate. So, these are the things which can be done, but you see that this cone calorimeter is not very big. So, sample sizes are limited. Now, I have another test facility called radiant panel test. Again, the concept is same. I have a, see, for example, if I have a vertical boards, etc., or for example, some laminated wood surface, etc., to find the flammability, I just mount it in a vertical manner like this, and again this is in a platform where I can put a load cell and monitor the mass loss rate. Now, to heat this, parallelly I keep a radiant heat units. Okay. Now, again I can give the required electricity so that the surface temperatures are controlled, and the heat flux imparted to this. So, I can vary the distance, I can vary the current or the temperature of the surface, and I can increase the current if I want to reach higher heat flux and so on. So, that again I can do ignition test, the flame, see flame I can ignite wherever I want, and the flame also spreads over this. So, flame spread test also can be done. Once the flame spreads over the sample length, entire sample length, the mass burning rate can be taken into account. So, to hold these radiant heat units, I will have a water cooled support. Okay, that is also incorporated here. As in the cone calorimeter, the gases which are coming out of the fire will again go through a collection hood and other points, gas sampling point, orifice plate, smoke point measurement, everything will be done in the hood. So, the hood and the associated instrumentation will be intact in all these facilities. Now, coming to the fire propagation apparatus FPA. So, here you see that the advantage of this is you can make it very big and you can go to huge fire facilities. Say for example, even 500 megawatts fire, 600 megawatt fire and so on. So, now the concept is same. I have a platform in which sample is kept, and this sample is kept over a load cell, so that when it burns, the mass loss rate is captured, and the sample is actually heated using infrared heaters. This is one of the option we have. So, you can surrounding that, then you can heat it. Now, other than what we saw, you can also have a flow rate of oxygen, air. See, for example, I want to increase the oxygen in the air. Say oxygen content in air is about 21% by volume. Now, if I want to make it 30%, I can do that. Similarly, I want to reduce it, I can also do that. So, I can mix nitrogen and oxygen in whatever proportion I want. So, that in a variable oxygen conditions, how the flame behavior can be studied. Now, this co-flowing, or we can also premix if you have a gaseous fuel, or in case of condensed fuel you can make it as a co-flow. So, now I can vary all these things, again get the hood, take the fire gases and analyze it in whatever way you want. So, the main advantage of this is you can go for bigger sizes, then you can also have co-flow of oxygen and air. The other things like measuring the load or the mass loss rate or gas analysis etc. will be same as in the previous cases. So, this is the fire propagation apparatus. Now, let us just summarize what we have seen. Ignition test basically can be conducted in FPA or cone calorimeter, and as I told you, the material has to be heated to a certain level. That means the heat flux, there is a heat flux coming into the material surface, there will be some heat loss from the material surface due to re-radiation, we have already seen this. Then there will be also conductive heat transfer within the material from the surface to the interior. But if the heat flux is not enough, then you will see that the material cannot be heated up. Correct. If the heat loss is more, then material cannot be heated up. The temperature will slightly increase and nothing will happen. So, increase your heat flux and try ignition. There is a critical heat flux at which you will see that the ignition source can produce ignition through a spark plug or any external source which is kept at a given distance, again based upon standards. As I told you, you cannot keep the ignition source very near to the surface of the material or very far away. We have to keep it at a location where the stoichiometric mixing has happened, or at least a flavor mixture is present. So, this critical heat flux data is tremendously important for us to quantify a material to be used in several applications. Similarly, surface temperature of the material can be recorded, and the ignition temperature, that is the value of the surface temperature at which ignition has occurred, that can also be taken into account. Okay, now as I told you in the beginning, thermal response parameter TRP can be defined using the critical heat flux, ignition temperature and the material property, thermal inertia, rho Kc. So, now main purpose of these tests is to vary the material composition. You can have some hybrid materials, come up with empirical correlations for getting the time of ignition. Okay. You know the application of the material. The material has to be kept in a particular enclosure or any application, and it may be exposed to some heat flux for a given amount of time. So, based upon that, you have to quantify the material such that it will not be ignited. So, that is the purpose. So, empirical correlation for time of ignition is obtained by using ignition temperature, critical and external heat flux values. So, critical heat flux and external heat flux values are, critical heat flux is coming from the test, the conical heater or the infrared heaters etc. External heat flux is any other heat source other than this can also cause heat flux to the material. So, now the correlation is very important. We can do it for several materials, and the thickness of the material plays an important role. If the material is very thin, then the heat conduction can be neglected within the material. So, we have already seen thermally thin material etc. If the material is thicker enough, then you have to take into account of the heat conduction to the material also. So, these are all the important characteristics of ignition test. Then another important parameter what we get from these tests are heat of gasification or pyrolysis. General gasification, it means pyrolysis gases are released from a solid material or vapors are released from a liquid fuel. So, this can be, so what is the heat required to do this? So, that can be carefully measured. Now, for this I can use in FPA air environment or nitrogen environment, inert environment, so that I can have a flaming combustion over the material, or just the gases are released from the material without causing any flame, because there is no air to burn. Fuel vapors come out, but there is no enough oxygen from the ambient, which is not supplied here. So, in this case, that is the advantage of FPA, where I can change the environment, and I do this, find the heat required for pyrolysis to occur. So, the heat required for pyrolysis depends upon the condition. Okay, if there is a fire, the pyrolysis will be different, the heat of pyrolysis will be different. But if there is only a heat flux there, but there is limited oxygen, etc. So, anyway, you have to know, based upon the fire heat flux, how much heat is supplied to the material in order to make it pyrolyzed. Now, second one is the mass loss rate. Mass loss rate is measured along with the values of heat flux to the surface, radiation loss and external heat flux. So, now using the mass loss rate measurement, then the heat flux to the surface, put some radiation sensors around this fire, so that you know what is radiation loss, and also capture any external heat flux is present. Based upon this, the heat of gasification is determined using a simple theory, and this heat of gasification is correlated as a function of molecular mass of substances. Okay. So, there are several correlations available in literature covering materials having molecular mass of 30 kg per kilomole to around 250 kg per kilomole. So, this is another application or another important data which we can extract from cone calorimeter or FPA. Then flame heat flux. There are standard procedures again to find this flame heat flux. As I told you, the flame heat flux is the important parameter, which is actually the part of the heat coming from the flame to the surface. Contribution to the heat flux to the surface by convection and radiation are determined by various materials, for various materials with varying surface areas. So, please understand that balance of heat and mass transfer should occur. So, this has to be quantified properly. So, what we do is, we vary the material, type of materials, material thickness, the geometry, and also the surface area, and try to burn it, and also we can vary the oxygen content in case of FPA, and know how it is going to affect the flame, how much flame heat is transferred back to the surface. Okay, now convective heat transfer coefficient, okay, for a flow field in FPA can be determined using the combustion of a simple fuel. So, if there is a flow of a product mixture which basically consists of CO2, H2O, nitrogen, some amount of CO, nitric oxide, etc. Okay, now when you burn a well-known fuel like methane, methanol, etc., you can calculate the product, because you know the products actually, and when I say methanol, it has a O molecule atom within the fuel. So, it burns quite nicely. So, what happens is, the convective heat transfer coefficient can be determined for this case. Okay, now what was seen is, if the oxygen mass fraction is increased more than about 0.3, then asymptotic behavior in the mass loss rate comes. So, the mass loss rate basically increases with the oxygen concentration. So, I can draw this. So, for example, this is the mass loss rate m dot, and this is the O2 concentration. So, for say this is 0.18 and this is 0.3. After 0.3, you will see that it actually goes asymptotically to a constant value. So, this is possible to do in a FPA and categorize what is the limiting oxygen concentration, lower value at which ignition can occur, or higher value where there will be an effect of increased oxygen concentration. Similarly, the material surface area also will contribute to the radiative heat flux of the flame. So, for example, if the surface area increases, the radiative heat flux from the flame will be increased basically. Again it reaches an asymptotic value. Okay, so, when the surface area is smaller, convective heat transfer will be dominating. When the surface area increases, radiative heat transfer will take over and convective contribution will decrease.